Okay, welcome back, friends. So, back with my hot mug of tea. So we're getting somewhere with this, right? We've got these birds flapping around, looking very fetching and attractive. Zoom up in here. Moving independently, they're not like clumping up together too much. You can see that they're kind of trying to maintain this radius of separation between each other. I think what I'm going to do is kind of what's been sort of customary up until now at this halfway point is to kind of walk through the code and add some more comments and make sure it's like super clear what this is actually doing. So in the setup function here, we create our canvas, or our window, more accurately. Load the image asset for the bird right there. Create a bunch of birds, like at random positions. And then sort of pick one bird, just the first one in the list, sort of arbitrarily, so that when we're on, we have these different debug modes, right? So that when we're on this sort of single debug mode, we need to pick one of the birds, which that sort of debug is enabled for. As we add more forces and things affecting these birds, it's going to be easier to visualize if we can kind of just isolate one like that. So these are just, okay, these are actually defined at the top. I added them again down here for one reason, which is that there's this thing called, it's kind of neat, called tweak mode. When we run in tweak mode, it allows us to kind of change the values of any constants and sort of tune these parameters in real time, which is a really nice way to kind of tweak, you know, like the range between the birds or any other kind of behavior that we want to play around in, right? So I can like push this radius up really high and then they'll really try and spread apart from each other a whole bunch, stuff like that. But this tweak mode, for whatever reason, only allows you to change you know, constants like this. Like it won't let me change the values of these variables because I guess in theory these are already set once when the program first runs and then they're not like set again. So yeah, that's just not how the tweak mode works. Let me do a little very common calculation here for how much time has passed. So let me draw the sky. Let me update and draw all the birds, and then this is just a bit of gubbins to make the debug mode toggling, or I guess more cycling, because there's more than 2 modes for this now. If you press D, we go from like off to single to all mode. Then where the really interesting stuff happens is in the update and draw functions here, so figure out let's do draw first. It's kind of simpler in a way. So each bird, when we create it, contains a sprite, and inside this sprite class we've got some logic which we borrowed from the previous stream where we made this 2-button brawler game, and this logic will track how much time has passed and cycle through the frames of this animation, which is what gives us that flapping effect. So if you really want to get into the details, I would check back the VOD for the 2-button brawler game, but that's kind of all this is doing. It's counting how much time has passed and then cropping out effectively a certain section of the image to draw based on that. So this is a useful, like, general purpose thing. I feel like it's not really the purpose of this stream. We're thinking more about how the birds move and their behavior. So this is probably something that we'll start pasting in and reusing, you know, in different streams in the future, possibly. Yeah, so the other thing we do is we update the birds, right? So to do that, we're tracking a few bits of basic information. That's purely visual stuff. This is like physics kind of state stuff. This is debugging flag. Yeah, so we initialize it with like no velocity and no acceleration, but then every update we do a load of calculations to build up the acceleration, which is kind of equivalent to figuring out what forces are acting on the bird. Those forces are, if the mouse is pressed, then we're going to kind of steer towards the middle, or steer towards the mouse, otherwise they're just going to kind of freely fly around. So we work out a vector from where they are to where the mouse is, and then we kind of scale that based on how intently they should be trying to follow that mouse, and then we kind of add that into that acceleration. Then we start applying a bit of logic to stop them from clumping up too close, which is called separation, and all this does is it goes through all of the birds. It works out, you know, how the direction and how far away the bird is. If it's too far away, then we ignore it. We're not going to try and avoid a bird that's like not even close. But if it's within a certain range, then we're going to kind of add a force on us, sort of in the opposite direction to the bird, which causes us to kind of move away from it. So we can start kind of building up a picture here, I think, of the forces that might be affecting a bird at any given time, right? So let's say there's another. I have to draw a bird now. Let's say there's another. So there's another bird over here. Then maybe it's going to kind of track the direction of that bird, and it's going to try and go somewhat in the opposite direction. Then if the mouse is like over here, then there's going to be a certain amount of attraction towards that mouse point, which kind of pulls it in this direction. Yeah, so we have these competing forces, right? We have repulsion, or separation, I guess it should be called. So we have attraction, like mouse attraction. We have separation. But that's not all there is to it, right? If you Google flocking, or there was actually an original paper, I think this was based on, called boids, there are a few different things that people often... Oh, you probably can't see this. There are a few different things that people factor into this to give it sort of more realistic behavior. So we've got this separation thing. Another thing that people look to do is... There's two main things. There's alignment and there's cohesion. And what alignment will do is it will say... Get rid of some of these things. It will say that if my buddies are near me and they're all flying in a certain direction, that's a bird, ignore that, then I'm going to also try and steer in the same direction. So unlike separation, which is based on like the position of these things, alignment says, hey, look at the nearby birds and then look at just the direction they're going and try and match my direction or speed with them. Yeah, and that causes, in theory, causes birds to kind of try and like line up facing the same direction. So if one bird starts to turn, the others will kind of start to turn with it as well. So it gives them a kind of, you know, this is how these things move. They kind of stick to each other's sides and kind of move around like that. So let's try and add in another bit of logic for this. So we need some forces here. We're going to call this alignment. these could have different strengths. These could apply at different sort of with different radiuses. I feel like to aid with the debugging, we're going to need to add some more debug drawing, but you know. So that's the separation radius. Let's also add the... If it's separation, you're like avoiding, right? So let's make it red. I feel like that feels a bit more intuitive to me. If we're trying to align, then... yeah, let's make it like yellow. I feel like that's kind of a neutral sort of implication. So we're going to align within that sort of area. Then we can do a bit of copy pasting here. Right, this is kind of what we're trying to achieve here. Which is probably based on, yeah, so probably the way this works is we work out all of our neighbors, we figure out the average heading. Yeah. So the way we work this one out is we kind of applied a force for each one, and that is kind of okay. But in here we kind of want to, I feel like it makes more sense to calculate the average angle they're all facing and then sort of try and steer ourselves in the same direction. Because if there's two, you know, if there are two of my buddies by me, or if there are five, I think the strength of the force overall should be the same. Yeah. So what I kind of need to figure out is kind of the average heading of my neighbors, right? Which kind of starts off at 0, and then if somebody is close enough to me, we want to find an average heading here, and typically the way to do that is to sum up all of the values and then just divide by the number of neighbors that you had. So the alignment there kind of 0. So I'm going to increase that because we found somebody nearby. And then all I'm going to do is add neighbors.add. It's going to add the velocity of that other. I should probably call this average velocity. That's kind of more actually what this is. And then I'm going to say if there was at least one bird within range. So if this count is greater than 0, you know, I'm avoiding some potential divide by zeros here. Then I'm going to say I kind of need to divide this by the number of neighbors I had, which is the same as multiplying it by 1 over that number. Cool. So this gives me that sort of average velocity, and then I kind of want to figure out the force from that. Which is going to be just taking that and then scaling it to the strength of alignment. So I've missed a bracket here, I think probably it just hasn't updated. There we go. Okay, so I think this will do what I want, but I would really like to have a better like debugging view of this like straight away. There's now like many different forces applying to this bird, so I kind of want to have a way to visualize those. Also then want to add this into the acceleration, of course. So I think what I'm going to do is, even though I don't actually need this alignment force I've calculated outside of this function, right? Like once I've applied it to the velocity, I'm kind of done. I think what I want to do is save the most recent alignment force like as a member of this class so that I can then debug it or view it, like visualize it when I do the debug drawing. So I'm actually going to move these things out. Probably gets easier if I actually have these as members up here. I can kind of assign these up here as well. No reason really why not to. So now what I feel like I want to do is to set this to 0 here. Just add it here so that this arrow is going to represent, you know, all of these forces together. And let's add it once here. Same here. I think I want to take the alignment force, set it to 0. Okay, so now we know those forces and we can in theory draw them here, and I think the way I'm going to do that is simply by drawing a line from the center point of the bird to okay, this may need to be scaled up to be visible. I'm not sure how big these forces will be. I think they will be enough. But hopefully this will help us to visualize if things are working internally as we expect. Oof. Okay, where's our? It'd be nice to just have one. Where's our one special debug bird gone? There we go. Okay, interesting. So I think this is doing kind of what we want. I believe it's a coincidence that that yellow line is lining up with the red radius, but let me try and screenshot this as a top point and see if it makes sense. So what's going on here? So yellow is for alignment, and if we look at its neighbors, I feel like it makes sense to me that, you know, this one's going this way, this way, this way, this way, this way, this way, this way. This way they are generally pointing in like this kind of direction, so that's where that comes from. So they're trying to steer themselves to align with those. Yeah, that works for me. That feels like correct in terms of alignment. And then we have separation. So we have who's in range. Yeah, it looks like these two are the only ones in range of the red circle. So it makes sense, right, that this one's kind of pushing it like this way. This one is then kind of pushing it this way. Yeah, so it's averaging out to push it kind of away in that direction. So these seems to be doing conceptually what we expect them to do. We can definitely tweak the parameters so that this looks more natural for us. Maybe I'll put the number of birds down again and we can play around tuning these parameters. There's one more major parameter to go, but even with just these two we should see some interesting effects, I think. Oh, I should remember to use the tweak mode. And I should remember to add the alignment stuff in there. Nope, don't run, tweak, there we go. Okay. Separation force is really quite strong, huh? That red line. Let's bring them back to the middle. We can start playing around with these maybe. So start to notice that they do seem to be lining up with each other and they just seem a bit more orderly and structured, right? I don't know if you're noticing that. Yeah, let's start playing around with these and tweaking these. What if we made the alignment like much stronger, but the separation like relatively weaker? Then pulled them in. Yeah, interesting. Once you get things like alignment, you definitely start to see they'll form like separate flocks, right? They'll divide into groups, like one will go this way and then some will follow, but then others will go the other way. So you get these kind of distinct groups and clusters, which is kind of interesting. Yeah, and birds will kind of get like drive-by pulled into one cluster because there's some birds fly within range and they're going in a certain direction. It will be compelled because of the alignment thing to like join them, right? So these two packs will end up merging. Yeah, they seem to have done that. This straggler here at the back, if I can get them close enough together, will eventually kind of get sucked in and they'll become one group most likely. Right? Yeah, they've kind of merged there. Nice. Okay, we're definitely seeing some interesting, fairly like natural, organic looking behavior going on. I feel like we can probably tweak this even more. It might be nice as well if I didn't hold the mouse, they'd just kind of be attracted to the center. I think I might do that. So if the mouse is pressed, then I'm going to do towards the mouse. Otherwise, I'm going to go towards the center point, which is width divided by 2, height divided by 2. So these width and height are just global things for the width and height of the entire window or the entire sketch. Let's call this target. Okay, cool. Now we don't lose them quite so easily. Interesting. So what I've noticed is that when they really clump up, the frame rate does start to chug a bit, and that's because if there are more things within range, there's more calculations going on. If I amp up the number even more, that's going to be a bigger issue. So I feel like it might be worth experimenting with trying to make this a little bit more efficient. Let's play around with actually outputting here. How long it's been since the last frame. We can kind of see how this really is performing. Bearing in mind I've got OBS and stuff running, so this is way slower than it might otherwise be. Well, that should be probably on its own line. I mean, it's not terrible, right? Like if you're looking at like 16 milliseconds, that's about 60 frames per second, but you can see it's quite variable because it really depends on exactly how clustered and close together they are. So there are ways we can potentially make this thing more efficient. If I up the number of birds, this is probably going to get way slower because the amount of work that's being done is sort of exponentially increasing. Yeah, so I think what I will do is try and introduce something to make this a little bit more efficient. And the way to do that really is with some kind of like spatial lookup structure. So yeah, maybe that sounds complicated. I'm going to explain exactly what that is and how that stuff works. Actually, this screenshot might be quite helpful. So we've got this world going on here. And in order for this thing to calculate who's nearby, it actually needs to check every single other bird and calculate its at least the squared distance to it, and then ignore the ones that it doesn't care about, right? Whereas what would kind of be nice is if there is a way to efficiently say, hey, give me all the birds like within this range, or within this range. And there are several ways to go about that. One of the simplest ones, and what I think I'm going to do now, because you know, many ways to do this could be subject of a whole other video. Would be to add like do something like dividing the world into a grid of sorts. You can imagine if the grid is like sized to be sort of in line with some of these circles, then I know that, you know, if I'm like lined up with a grid cell like this, then I only need to check people. I only need to check things which are like in the same sort of grid cell as me. If I'm one like this, then okay, if I'm sort of on the edge or on the corner, then maybe I need to check like the neighboring cells as well. But the point is that there's a way where, given the range I'm looking at and given the size of the grid, I can figure out, okay, I only need to check within like a reasonable number of cells of me, which to an extent gets rid of this crazy like exponential issue. Issue being that, you know, if I have 10 birds in total, then each bird needs to look at 9 other birds, or actually it looks at 10 other birds and just ignores itself, so that's 10 times 10 is 100. But if, you know, if there's 1,000 birds, then there's like 1,000 times 1,000, so it's 1,000,000. So you get this big curve of how much work needs to be done. Whereas with this grid system, it's a bit more like, as long as the density sort of stays the same, it's a bit more of a linear thing, so it doesn't get out of control quite so easily. So the way I want to do this is by dividing the world into a grid, having each, but potentially multiple grids at different sizes, but I think we can probably just pick one size for now that works. And what I kind of want to do is each frame have the grid emptied out, and then just have the birds once per frame say, hey, I'm in this grid cell. So then when other birds are trying to look for people nearby, they can just check certain sets of like neighboring cells. So I'm going to create another tab for this. I'm going to call it let's call it a spatial grid, because that sounds kind of cool. And this is going to contain birds. It's going to be kind of array. So it needs a bit of information, like it needs the cell size. It also needs well, the one issue is how we handle stuff on the boundaries, right? Like in our thing right now, birds can actually go off the edge. There's a kind of nice way to handle that, whereby if a bird goes off the edge of the sketch, you just wrap them back around to the other side, which means things are always nicely within the grid. So I think I may implement that like super quickly just now, whereby sort of wrap the birds around the grid. So we say if let me just say we may get some weird effects at the boundaries, we shall see. So what happens when this bird comes off the side? It seems to be okay. I'm sure there's some slightly weird, like physically incorrect behavior going on. Actually, it's only wrapping in one direction, isn't it? So if they go off the top, they're just straight up going off the top. So instead I'll say this should kind of do what I want to handle all four kind of sides a bit more cleanly. now if we have them fly off the top, they come straight back in the bottom. Okay, cool. That's a kind of hacky way to constrain them to this grid, but I think this is probably for the best because it gets around a few edge cases I don't particularly want to deal with. So, nevertheless, right, we still need to know its size in each dimension. Yeah, that's probably enough to begin with, so when we construct it, let's pass those in. Let's remember those things first of all. Okay, then we basically need to allocate like an array for these cells, right? And what's a cell going to be? A cell is almost certainly just going to be a list of birds in this case. So, going to be something like an array of list of cells. Okay, it's kind of janky, but we're an array of list of birds. I feel like this could be more descriptive by calling it like num cells in each axis. Cool. So we need to, okay, how many cells are there in total, right? In this case, it's just num cells x multiplied by num cells y, because this thing's in a kind of 2D grid. So and to be honest, we could probably calculate these ourselves just based on the width, right? So we need at least as many cells to like cover the width of the screen. So if the screen's 100 pixels and it's like 10 cells, each cell is 10 pixels wide, then it means we need 100 divided by 10, or 10 cells in that dimension. So we need to say something like width divided by cell size. We need to deal with if it's not an exact round number, so we should probably round up, which is what the seal function will do for us, because we want to have, you know, we don't want like a grid that like doesn't quite reach to the ends on either side. So we want to, if we need one like extra cell on the edge, then that's kind of fine for us. That's the total number of cells, and then well, having a brain fart here on the syntax for allocating this kind of thing. Oh, okay. Interesting. So I just need to say kind of a Java generics quirk here. Oh. Screw it, let's cheat. Okay, this is kind of weird. I should kind of draw what I'm actually doing here. It's not super intuitive, perhaps. So what we ultimately want to represent is this 2D grid. But each element in this grid itself is actually like a list. And the way we're storing this grid is not as a 2D thing, but it's actually as itself a list. But then each entry in the list is itself a list, so a list of lists like this. So this is like, if you think of the coordinates, this is like 0, 0, which is this one here. This one's like 0, 1, which is like this one here, and this just continues like that. So that's the kind of structure we're making. It's kind of janky, but this should do what we need. And what I want to do is for each cell here, I'm going to pre-populate it with an empty list. So an empty list of birds. Cool. I feel like what we're also going to need is a function to like clear out this whole grid, because what we're going to have to do every frame probably is have, I mean there's other ways to do this, but I think the cleanest way is every frame have the entire thing emptied out and then have the birds like re-register themselves in whatever grid cell they currently happen to be in. So we'll do something like empty, and then all we do there is we empty all the internal lists. We empty the cell. Okay, then what we also need to be able to do is add something to this. We might as well start. Maybe not. Okay. You know, where's the object and where is it at? First thing we need to do is find out which cell it needs to go into, which means we need to handle the case where this is sort of out of bounds of this grid. So we're going to say if x is less than 0, or y is less than 0, or x is greater than width, or y is greater than height, then it's kind of out of bounds. So not the ideal thing, but I'm going to just throw an exception. Okay. Otherwise, we know we're somewhere inside this list. So now we need to find out what's the sort of ID of the cell, right? So Again, going back to this kind of diagram, if we have our grid like this, then this is like, you know, x is 0, x is 1, x is 2. This is like y is 0, 1, 2, 3. But in terms of their position in this list here, they're kind of numbered like this, like 0, 1, 2, 3, 4, 5, 6, 7, 8. So we need to be able to convert from like, you know, cell like 2, 1 is actually in like slot 5 overall. And the way we do that is a bit of arithmetic, and all it is x plus y times well, the width, or whatever the width is here. That's because every time y increases, we step down a whole row, which effectively means we add 3 in this case, right? 0, 3, 6. So the width is then 3. Then we'd have x is 2, y is 1. So 2 plus 1 times 3 is 5. That's how we get that coordinates. This again is a very super common thing for sort of mapping a 2D structure that's actually stored in like a flat list. Happens all the freaking time. So it's just, so well, the cell x is going to be x divided by cell x divided by cell size. Cell y is going to be y divided by cell size. The reason here is if we've got our big grid, you know, if these are like 100 pixels wide here, if we're at like pixel 120, then it means we're in, you know, like 1.2 grid cells along. If this is grid cell 0, this is grid cell, you know, x is 1, and we just kind of round it down. So this is like 1.2 round down to 1, and it tells us, gives us this whole sort of range here. Cast this to an integer here, which effectively will round it down. So and this is again that same formula we just worked out here in effect here. It might actually be nice to have a little function to get a cell. We could do something like this. For convenience, saying that we'll look up, given the kind of cell coordinates, it will give us the actual list for that cell. So let me register this bird in there. Cool, so that's done. So this will do that for us. Okay, let's check actually that everything gets registered as we would hope. So we can do something like okay, something else I should probably be doing here is that calculating all of these accelerations and then actually moving the bird probably shouldn't happen all in one function. And the reason for that is that you know, if we got 2 birds here, in theory, what we want to be simulating is like these are both like moving and reacting to each other simultaneously, right? But what the code actually does is this bird A will like look at bird, if this is A and B, this bird A will look at bird B and go, oh, I want to move away from them, and it will update its position over here, and then bird B will check, and now bird A is already like moved away. What we kind of want to do is have each bird look at each other, figure out how they're going to move, and then have those moves happen simultaneously. So that makes sense. So that they, it's not like we update the position of one and then this bird is now looking at the new position, even though in theory this is happening at the same like instant of time, and it should be like a proper simultaneous turn, right? It shouldn't matter what order in the list of birds they are. So the way around that, generally speaking, is to calculate the acceleration before as a separate thing, right? Just as not part of update. So all I really need to do here is do the acceleration calculation separately. So now we will do this in like a two-phase thing. So we do all the calculations, they figure out what their acceleration should be right now, and then is when we actually update and apply all that stuff. Seems good to me. We also want to actually create this grid thing. I'm going to create it in setup because we don't know how big it's going to be until we've determined the size. And what should the cell size be? I'm going to say, I don't know, let's say 50. I mean, this is definitely a tunable parameter, and you probably want to experiment or do a bit of theory crafting to figure out what's the actual optimal grid size here, but 50 probably works. I mean, it might even make sense to have different grids used for separation and alignment. That may end up being more efficient in some cases, but right now I think this is probably all good. So let's populate that grid. Empty the grid. And then we're going to add all the birds into it. We're going to add the bird. We're going to add it at X and Y. By the way, if I'm going too fast and this doesn't make sense, please do drop a line in the chat and I will slow down or like re-explain or go over anything that you want to have it more detail about, or just anything you're generally interested in. So it feels like we're doing a whole lot more work here, right? Like every time we're emptying this whole grid and then we're going through the birds one by one and like adding them all back into the grid. This is a whole load of bookkeeping we're doing. But again, I'll remind you of our little graph we had, right? Where if the number of birds, we'll call that n, is going up, then the amount of time kind of goes up exponentially. And even though this grid is a load of bookkeeping, there's no like exponential factor to it, right? We clear it out, and that sort of amount of work is kind of proportional to how big the grid is or how many cells there are. Then we register all the birds in, and that's just proportional to the number of birds. So, we're now, everything's a bit more like straight line. And maybe there's a bit of overhead to begin with, but we'll reach a point where the explosion in time required to handle all of this stuff without this kind of bookkeeping would actually overtake the overhead of the bookkeeping, if you like. Again, that's something you should measure and figure out where the sweet spot is, but anyway. I kind of want to throw a debugger in here. So that after the first go around, after the first frame, This is the first time, right? The grid's already empty. But if I continue and let it loop back around again, now if I look in the grid, so it gives me this handy variable inspector, I can actually start looking inside here and start looking in these cells directly. Say that, okay, there's nothing in the first cell, nothing in the second cell. Third cell, it's got a bird in it. Yeah, so that probably makes sense, right? The third cell is probably like here somewhere. It might also make sense to like debug draw this grid. I guess the next cell's going to have this bird in it probably. Okay, there's two, like maybe this gets caught in as well. The next one, maybe it's going to have those three, or maybe that's not, maybe it's the space between. Maybe that's three. Okay, so I should probably draw the grid for debug purposes, but it seems to be correctly like allocating things into the right buckets. Right now we're not actually using the grid for anything useful, but you know. Let's actually add a debug draw function here. And all that's going to do is draw some lines. So x equals 0. Draw lines kind of top to bottom for the x. Let's just do these like kind of grey color maybe. So this is going to be a line starting at x cell size 0. So if this is like the third cell across, they're going to be like 1, 2, 3, and 0 down to that same point with the height. So this is going to be like a vertical line, top to bottom. Do something very similar with y. And then I can just say too much JavaScript, letting that crept in there. Cool. Let's see if this does what we hoped. So if I turn debug on, okay, we're seeing this grid. So that seems nice. And I'm kind of trusting that the grid is things are getting allocated to the right square. So now what we need to do is actually use this grid to more efficiently, if I print screen again, no, they're super clustered up there. Let me find a more opportune moment. Yeah. So what we kind of want to do now is when this thing's checking for stuff in the red circle, what we effectively need to do is say, okay, I'm only going to check for birds in these cells, because those are the only cells that like overlap with the red circle, right? And then for this yellow one, I know that I'm going to need to check in like maybe these cells. Like maybe I could be super smart and like try and chop out like those corner ones if they're not totally overlapping, but I feel like that's more trouble than it's worth, and I'm just going to kind of do like a, I guess like a bounding box, you could call it. So how do I figure this out? I need to work out the kind of coordinates of, let's say we're doing it for the yellows, I need to figure out this box. The name for what we're doing, by the way, is like, this is like a spatial acceleration structure, you kind of call it, and this is also kind of referred to as like a broad phase collision. So the broad phase allows us to, with some like false positives, right, like these aren't in range, it allows us to like prune down the stuff we're going to have to check, and then the narrow phase will do the actual distance check, and that will filter out the stuff that's actually outside that circle. So you call this like broad phase. It's kind of like collision detection, more or less the same thing, and then this would be like the narrow phase, or like the actual final accurate stuff. And you often use like a bounding box to do this broad phase and just filter out the really obviously irrelevant stuff. So kind of all we need to figure out is like the top, you need to think about the top, bottom, left and right of this little thing, right, which is easy enough. We're just going to take our position, we're going to subtract the radius in the x direction, we're going to add it over here, and again with like a in the y direction, so we can kind of get like a minimum x, maximum x, minimum y, maximum y, and then we can use that to figure out which cells we actually care about. So I feel like I kind of want to put this into the grid itself. It'd be nice to just say something called like a query, right? So what's the x, what's the y, and what's the radius? How far are we going to do that? And we're going to give back a list of birds. So we kind of need to create a new array list. If you get really deep into optimizing Java, you probably don't want to be creating new array lists, but that's kind of beside the point. Let's give it an initial size, kind of a guess at how many things might generally be within that sort of range. Then we need to figure out what cells we need to look at, right? So basically we're looking at something like this. I heard the rumble of thunder outside. These are actually floats. Okay, so we have like the kind of bounding points here. Now we need to just figure out, okay, what cells are these things in, I guess. So it's kind of as simple as saying min cell x is equal to min x divided by cell size, and then sort of rounding this as well. Do the same on the y-axis. Okay, so that should give us those bounds. And then we kind of just need to loop over all of those cells and add any birds in there into our big results list. So starting at min cell X, if it's less than or equal to max cell so looping around in that axis, do the same in the y-axis. So we'll go over every cell in turn in this bounding box. Then we could just dump out a list. Hey, Ita, how's it going? So what we're doing right now is we're trying to figure out a way to optimize this whole thing and make it a bit more efficient. I don't know how much you saw there, so I'll quickly kind of explain. Yeah, so what we've done is not good. What's up? Yeah, but what we're doing is we've kind of created this like grid, and then every bird is now sort of. Oh, thanks. Yeah, so we're not an affiliate yet, so we don't have all of that stuff. Yeah, I honestly don't know how the whole subscription and affiliate stuff works in like super great detail. I know once you become affiliate, there's a whole lot of more options, like the channel points and stuff you can create, but I don't think we can do any of that right now, right? Coffin dance. Okay. Have you got bleeding fingers or something then? Anyway, what we're trying to do here is we've created this. We're getting to the point where each bird, right, needs to figure out where its close like neighbors are in order to work out how it's going to steer itself around. But it's it can be inefficient, right? Because there's a whole crap ton of birds around here. So what we've done is we've divided the world into a grid, and we're keeping track of, you know, which birds are in which grid cell. So now, when we want to find all the birds close to this one, yeah, I know. Yeah, so we're mostly on par for those. It's just the 50 followers, which I feel like is a matter of time. We're slowly gathering followers, but I feel like at some point in the next few weeks, couple of months, we'll definitely cross that threshold, I think. Yeah. Anyway, so what we're doing, we divided the world into the grid, and now when we want to find out who's within this certain range, we've sort of optimized it so we're only ever checking out birds which are within grid cells which like overlap with that circle. And this is a very common way to like optimize this kind of stuff. Please don't do that. It's just not going to help us. It's just no. Okay, so we've now got this grid. We can say, give me all the birds within a certain radius. So now let's maybe try switching over to doing that. So now rather than passing in all the birds, we kind of just need to pass in the grid. And now we can query. Yeah, thanks. Yeah, if you can spread it around in that way, that would be super, super appreciated. If it's real people. Okay, so now we have this handy function, which assuming this all works, should be able to quickly and efficiently give us all the birds within, or help filter down birds which are like definitely out of range for us, which, if all goes to plan, will make this a bit more efficient. So you can see now, like, the time between frames, this is milliseconds, is like kind of all over the place. It's kind of weird. Maybe something else, like having an effect here, seems to have like a regular pattern to it. But anyway, we've now got this grid in place, and we can see if that has any effect. Oop, did not like that. Probably something exactly on the width or the height. And, oh, okay. So we need to make sure that it never is less. Yeah, so this thing here, if we're looking at a bird like right on the edge, it could be kind of trying to consider, you know, if this bird here is looking for all things within like this radius, then it may be trying to refer to like a grid cell which is like, you know, off the edge here, which we really don't want to happen. So that's probably happening here, so we want to make sure that this is never less than 0. We need to make sure that this is never off the edge that way. Okay, I feel like that's probably what's going on there. I think as well, when we wrap these things around, if they're exactly equal to the width, then that's also a problem. So let's do this. Okay. Cool, now let's try some debugging to see if anything funky is going on. Perhaps here, when we calculate the acceleration, let's just make sure this grid is doing something sensible for us. Okay. Jump into this code. So the bird's at a certain position, certain radius we're looking at. Let's see what it figures out from this. Okay, seems to be picking a reasonable range around here. Yeah, nice. And then it's picking only a certain range of cells to look at, which seems sensible. So we know there are 250 birds in total. There are probably far fewer that this is going to check through. Yeah, check through like 3 birds. So that seems way nicer. Just run this again and play around, see how this looks. Hey, small indie dev. Thanks for the follow. Thank you. Welcome, welcome. So what we're doing right now is this kind of flocking simulation. I don't know if you're familiar with this kind of thing, but we've got all of these little birds flying around, and they're flocking around trying to maintain their distance from each other and also follow my mouse. Also kind of trying to align with each other, and you get this cool flocking effect here. It does seem kind of natural, right? Like, I did not. Yeah, right. So you see, like, different clumps of birds will separate off and get lost from the pack, but then they'll kind of end up being sucked back in, right? If I kind of fling them around a bit more with my mouse, you'll kind of see that happen, right? They get broken off, but they get absorbed like back into the flock because of these. They're always trying to like line themselves up with their buddies and stuff like that. Really? Okay, I thought that was you being funny there, but I will try and enunciate more clearly. I think whoa, that was kind of crazy. I think something else kind of cool to add here would be, what if you get these things like an obstacle to avoid, right? So if you put like a block, if you put like a block or something here, well, hopefully I don't get banned from Twitch for that. It's just an accent. Yeah. Make them avoid ball. Okay. Let's find something for them to avoid. Okay, now I need I need an image. So I do not want to try Azure, a bird. See, I'm not gonna bring Paul back into this because you got kind of carried away last time, and yeah, let's not go down that road. But I would like some kind of a thing for them to avoid. Okay, I'm down. That's cool. So, for everyone else's benefit, this is what we now, for some reason, have decided is part of this simulation. I kind of need him to be like circle-shaped. Thankfully, his head is pretty damn circle-shaped anyway, so let me just take an eraser to him. Oh, that's so weird. That's so weird. What I really need is something like really round. Like this is maybe round enough. He's also cropped at the top of his head. Okay, yeah, I mean, if you can find me a really good example, then we can throw that in. Okay, I'll trust you to. Okay, wow, you're fast with this. Okay. Okay, that's kind of cool. I don't know what this is, but oh, they keep coming. That's just scary. Oh, is this? Wait, is this Squidward? Who is this? Okay, that makes sense now. So Okay, that's just too creepy. I'm avoiding that one. That is just weird. Can't believe I'm tracing Squidward's nodules. This is not a normal thing to be doing on a Friday evening. Okay. Right, that's kind of why I chose it. It's because it's weird, but it's not making me like personally that uncomfortable. Okay. Okay, there is. He's gonna have a flat head as well. There's Squidward. I'd be surprised if you did, Eater, have a not weird one. Anyway, here's our little dude. He's kind of too big. Okay, well I've cut Squidward out now. I'm kind of happy with this. It is pretty circular. This will do. This is round enough, I think. So I'm gonna need to load in Squidward. Just for you, Eater. Oh, I can't pull the tab off. What's going on? There you go. Look at that. That's something special right there. Yeah. Okay, so I've got to load Squidward in. Let's put Squidward. Where should we put him? Let's draw. Let's draw Squidward, I suppose. Make sure we draw him centered. Hey, Big Bro. Thanks for the follow. You've stepped into something profoundly strange. Okay, you know Yuta though, right? So it's probably you're probably used to this stuff by now. Yeah, okay, then you're definitely totally ready for this. This is going to be something tame. Okay. So anyway, what we're working on is a simulation of these birds flocking around, like all the forces on them. It's a somewhat realistic simulation of like how birds actually form formations and flocking in the sky. What we kind of want to do them now is have them avoid Squidward, because who could blame them for not wanting to get too close to that guy? So Let's specifically give them some Squidward avoidance code. So let me take a screenshot of this. Actually, it's gonna be useful for a little diagram. Okay. So if you are a bird trying to avoid a Squidward, what you kind of need to know, let's take this bird here as our example. What we kind of need to know is what direction is Squidward, so we can go in entirely the opposite direction, because obviously that's what we want to do. So we need to kind of subtract Squidward's position from our position. That gives us this arrow. We kind of need to just point it way over in the other direction, and that will give us our Squidward avoidance. Equal to that gives us the vector to Squidward. Then we kind of need be nice to have the distance, or at least the square distance of Squidward. So how big is Squidward? What's the range of repulsion for him? I think it's like where are we? Yeah, he's like, say, 80 pixels around, something like that. Maybe more like 60. Oh, let's call it 80. What are you doing? What are you doing, Yuta? I just need to take a moment to realize that I'm a man in his early 30s who's just written, you know, a formula to calculate the square distance to Squidward. This is there must be something wrong about that. Anyway, what's our like Squidward range? Or his Squidward size? We said that was going to be like 75 pixels, right? So if we're far enough away, then we're going to ignore him. But if we're within range, then we need to avoid him. Yeah, right. That's maybe that's the next thing. Okay, find me the cup of tea, and we'll make it happen. So if we're within range of Squidward, I feel like I still can't get used to saying that. If we are within range of Squidward, then if we're like here, like right on his face, we really need to get the hell out of there. If we're like just on the edge of his range, then maybe it's less significant, right? So if our distance to him is like 0, then we need to really go like full speed away. If our distance is just on the edge, then less so. And that will cause them to like generally swarm around him, hopefully, and hopefully we get a cool effect from that. So let's say we can use the map function on this. So it's going to map this square distance, which can be from 0 to which starts up in the range from 0 to Squidward size squared, and we want to map it from so if you're really, really close, we want to like super avoid him like 1000 strength. So if our distance is at 0, then we want to avoid him at full strength. Otherwise, we want to avoid him at 0 if we're just on the edge there. Cool. Okay, I'll save that for later. That's very appropriate. That's okay. So we've worked out a ratio where essentially how much we want to avoid him, and then all I need to do is say, in fact, it's exactly like this avoidance here. And we say we apply a force, which is going to be exactly the same way. Okay. Okay. Okay, we can see something's going on here, right? Like they are kind of clustering around, but they are making some effort to avoid going too close to Squidward. I feel like we can probably make that like even stronger. First, let's give him a bigger range. Let's make that like 5 times more powerful. Because I want him to almost be like a solid barrier. Yeah, there we go. No one's touching Squidward now. So they are happily like flying, orbiting around. Squidward can like, so we can create like a flock over here, right? Have them all clump up together, but then eventually, if they go anywhere near Squidward, he's gonna like, he can split this whole flock in 2. They'll go around him and then reform on the other side, which is kind of cool. And you, Chav, thanks very much for the follow. Wow, Yeet is bringing him in. He's also kind of responsible for this monstrosity. We now have flocking birds avoiding creepy Squidward. It also looks like someone's chopped his brain pan open. He's been Hannibal Lectered or something. Yeah, so we can also get a little bit of a debug view into what's happening. We can see that each bird has certain forces acting on them, so this yellow thing is its inclination to kind of stay aligned with its buddies. That's kind of what that yellow represents. The red is it's trying to maintain distance from its friends, so it prevents them from like clumping up too much. And then there's this very powerful force which prevents them from going anywhere near Squidward. Okay, I guess onto the cup of tea, and then we're more or less done at that point. What's going on here? This has been like badly green screened on. if there is a hole in this cup of tea. Now I need to repair this teacup. It's very off topic. That'll have to do. Just throw this tea in here. Code's getting messy, so I'm just throwing this stuff in super quick. Okay, what I'm doing now is rather than having the birds check if the mouse is held themselves, they're just going to always go towards this. Seek position. Okay. Place my teacup around. Yeah, I mean, I feel like we've created some kind of masterpiece here. So then the final thing to do maybe is just play around tweaking these parameters a bit more. Yeah, I mean, I have to give you some credit, right? I mean, this whole deal. Oh, might playing around, reducing the number of birds a bit. Okay, I think that's kind of where I will leave it. I'll leave it tonight. Thanks everyone as always for joining us. I'm gonna throw a few links in here if people are interested in finding out more about the game or following on with these streams in the future. Yeah, so I've started like regularly throwing out polls for these, so I think I'm going to do that each week now. So if anyone's interested in these things, flocking simulation 1 this time, we'll have another option added to the list for next week. Probably do the vote on Thursday. Yeah, tomorrow can't happen. I've got other stuff to get, other work that needs to be done. I'm kind of trying to do this a regular thing, like every Friday now. Thanks, Yuta. No, I do appreciate you like inviting people in and stuff like that. So. Thank you. Yeah, appreciate it. Okay, until next time, take care everyone.